Welcome to Science Pills, and welcome to you, the listener, to a highly specialized, totally custom-tailored deep dive into the very fabric of the AI landscape as it exists right now in early 2026.
Yeah, we have a massive amount of ground to cover today.
We really do. Our mission today is to dissect this definitive, honestly, earth-shattering inflection point. We're looking at the exact moment the tech industry basically woke up, looked at their balance sheets, and collectively abandoned the whole bigger is better scaling gospel.
Right. They traded in those massive trillion parameter behemoths for something infinitely more elegant, which are small scale reasoning models or SRMs.
Exactly. And it's a profound structural paradigm shift. To map this out, we are synthesizing a really formidable stack of sources today.
We're pulling from the absolute latest technical research, specifically MIT C-Sales Disciple Law Framework and the foundational papers on tiny recursive models.
And we're cross-referencing all that academic theory with the harsh economic reality, using industry intelligence from Gartner, global data, and some very aggressive edge computing market analyses.
It's the only way to get the full picture, really.
Okay, let's unpack this, because the hook here is absolutely wild. We're looking at a reality right now where a $6,000 one-time hardware investment is actively, aggressively replacing $4.2 million monthly cloud compute bills.
It sounds impossible until you run the numbers.
Right. And the smartest intelligence in the room is no longer the model that, just memorized the most internet data. It's the one with the most structural mathematical precision.
It really is the end of an era. I mean, for the better part of 5 years, the entire technology sector was governed by a single, undisputed religion, which was the scaling laws.
Oh, absolutely. The dogma.
The dogma dictated that intelligence was just a direct, linear function of computational brute force and massive data set ingestion.
Yeah, the strategy was basically entirely devoid of nuance. If a model was hallucinating or failing at some complex logic, the prevailing solution was simply, well, throw another trillion parameters at the architecture.
Exactly. Feed it another petabyte of scraped data and hope it gets smarter.
Right? It was just a sheer thermodynamic arms race. But I'm looking at this MIT Future Tech Lab report, and it completely shatters that illusion. They didn't just suggest the scaling laws were slowing down. They proved the existence of a hard scaling wall.
A literal wall. They modeled the performance gains against the compute required, and the physics of the diminishing returns are just brutal.
Like, you pour in exponentially more megawatts of power, you double the physical size of the cluster.
Then you extract maybe, a fraction of a percent of actual reasoning improvement?
Barely even a fraction sometimes. Yep. And we are seeing the capitulation to that scaling wall in the actual architecture of the frontier models themselves. Like, look closely at GPT-5.
Oh, it is undeniably a marvel of monolithic engineering. But if you analyze its inference pipeline, it is built entirely on a routing architecture.
Right, the router. It operates using main, mini, and nano modes.
Yeah, it acts as a dynamic traffic controller, actively deciding which tier of parameter count to engage for any given user prompt.
And that router is the ultimate tell. I mean, they wouldn't build a complex triage system if it wasn't strictly necessary.
No, of course not. That architecture is a proactive, very public admission by the giants that they cannot afford the thermodynamic cost of using maximum reasoning power for every single query.
Exactly. Trend Micro's latest market analysis actually captured the absurdity of the previous era perfectly. They pointed out that using a GPT-5 class model to format a spreadsheet or just draft a standard email is the equivalent of hiring a Nobel Prize-winning physicist to handle your routine data entry.
The compute overhead is financially ruinous.
It really reminds me of the automotive industry's obsession with muscle cars back in the late 20th century.
Oh, that's a good comparison.
Right. For decades, the only engineering solution to wanting a faster car was just to drop a heavier, more gas-guzzling V8 engine into the chassis. Just pure, inefficient combustion.
And eventually you hit the limits of physics. Weight, fuel economy, heat.
Exactly. The industry had to transition to hyper-efficient, precision-engineered electric motors. The footprint is a fraction of the size. They are practically silent. But the immediate torque and the actual performance on the road absolutely obliterates the old brute force engines.
That analogy holds up structurally very well. I mean, the competitive arms race hasn't slowed down. The battleground has simply shifted.
Right. We've moved from competing on raw scale to competing on architectural elegance.
But I know a lot of people are looking at this timeline and something doesn't quite add up.
Oh, totally. I need to push back on this myself, because if a highly optimized small parameter model is demonstrably better and cheaper, It implies the entire arms race from 2023 to 2025 was fundamentally misguided.
Right? Did the industry just burn tens of billions of dollars in venture capital?
And gigawatts of electricity.
Hmm.
Just chasing a brute force illusion. Was it all a complete waste?
Well, no, it wasn't a waste. It was a necessary prerequisite. The massive models were really the only way to prove that zero-shot capabilities and deep semantic understanding were computationally possible in the first place.
Oh, I see.
More importantly, those monolithic models essentially became the teachers. We could not have engineered the hyper-efficient SRMs we have today without the massive giants laying the groundwork, mapping the latent space, and generating the incredibly high-quality synthetic data required to train the smaller networks.
Ah, so we had to build the massive supercomputer just to understand the physics of how to shrink it down into a microchip.
Exactly. The giant models are essentially the scaffolding.
But if scale is dead, we really need to look at the actual scoreboards. Because deploying a cheap model is only economically viable if it can actually perform the logic required by the enterprise.
And this is where the migration of pure System 2 reasoning into small parameter counts completely rewrites the rulebook.
System 2, meaning the slow, deliberate, logical stuff.
Right. For years, the assumption in cognitive architectures was that System 2 logic, that multi-step deductive reasoning, required massive network depth to sustain the computation.
You needed a huge brain just to hold the thoughts.
Okay.
But the Artificial Analysis Intelligence Index v4.0 tears that assumption to shreds. Let's look at GLM-5, which is an open-source reasoning model.
Yeah, it recently achieved an intelligence index score of 50.
Which is wild. That score outright beats the GPT-5 mini variant in highly specific agentic workflows. When you put them head-to-head on coding benchmarks like Scicode, GLM-5 is hitting 46% accuracy compared to the mini model's 39%.
And the delta becomes even more aggressive when you look at specialized tool use. Take the Tau-squared bench, for instance.
Oh yeah, the telecom test.
Yeah, it tests complex telecom network navigation and multi-step API integration. GLM-5 scores an astonishing 98%, while the Frontier mini model languishes at 68%.
98 versus 68. That's a bloodbath.
It really is. The data clearly indicates that structurally sound specialized logic loops consistently dominate generalized mini-models when you deploy them in actual production environments.
And then you have Liquid AI throwing a massive wrench into everything we thought we knew with their TeleFM2 2.6B XP model.
Yeah, 2.6 billion parameters.
That is microscopic. Yet it is outperforming models 263 times its size. It's logging at 82.4% on GSM-8K, the math reasoning benchmark.
Which is impressive on its own.
But here is where I get genuinely confused. It's scoring 42% on GPQA, that is graduate-level physics, biology, and chemistry.
Right, incredibly dense subjects.
And a model that's small fits entirely into 650 megabytes of memory. That's smaller than a mobile operating system update. It physically cannot store the factual knowledge required to answer graduate-level physics questions. So how is it passing the test?
What's fascinating here is that we are witnessing the definitive decoupling of reasoning architecture from raw knowledge retrieval.
Decoupling them entirely.
Yes. For years, we conflated the two. We assumed an AI could only reason if it had mathematically memorized the entire corpus of human knowledge within its weights.
Because that's how the autoregressive prediction worked,
Yeah.
right? It just guessed the next word based on the frequency of the internet.
Exactly. But benchmarks like GPQA on a 2.6B model prove that reasoning isn't a magical emergent byproduct of memorizing Wikipedia.
Right.
Reasoning is a distinct mathematical engineering problem. The model isn't storing the textbook. It has learned the structural logic of how to process the variables presented to it in the prompt.
So it's not a database, it's a calculator.
No.
It doesn't know all the facts, but it knows perfectly how to manipulate the facts you feed it.
That's a great way to put it.
But to get a model that small, to execute logic that complex, the underlying math has to be radically different. I mean, we can't just be using the same transformer architecture from 2017.
Oh, we absolutely aren't. The primary mechanism allowing these small models to punch so far above their weight class is the complete abandonment of externalized reasoning.
In favor of what?
In favor of recursive latent space computation.
Okay, let's really dig into this, because traditional LLMs relied entirely on chain of thought, or COTI.
Right.
If you asked a model a hard logic puzzle, it had to explicitly write out its thinking process, token by token, word by word, into the chat window before generating the final answer.
And external chain of thought has two fatal flaws that make it fundamentally incompatible with high-efficiency edge deployment. First, it is an absolute nightmare for token economics.
Because you're paying for every word.
You are burning massive amounts of compute cycles and paying API cost just to generate the text of the AI, thinking out loud. It is pure overhead.
And the second flaw is the brittleness of symbolic decomposition.
Exactly.
If the model is writing out a 10-step logic chain and it hallucinates one minor mathematical error in, say, step 3,
The entire autoregressive nature of the model forces it to condition all future tokens on that specific error.
right, the rest of the chain completely collapses, and it confidently delivers the completely wrong answer.
It is an incredibly fragile way to compute logic. To solve this, researchers in early 2026 introduced generative recursive reasoning models, or GRAM.
GRAM, okay.
Instead of forcing the model to decode a rigid reasoning trace word by word into text, GRAM executes its iterative computation entirely within a continuous high-dimensional latent space.
Oh, a continuous latent space. I know this implies moving away from discrete text tokens, but what does the actual computation look like inside that space?
Think of it as treating reasoning not as a sequence of words, but as a stochastic optimization problem. The model establishes a solution trajectory.
Okay, a trajectory.
It starts at an initial mathematical state, z0, and refines that state over multiple recursive internal steps until it reaches an optimal final state, zt. It is mathematically refining a vector, not typing a sentence.
Oh, wow. And it anchors this process using a dual-level latent state. It's essentially tracking two separate realities at once.
Exactly. The high-level state functions as an abstract reasoning anchor. It maintains the global context of the problem, the ultimate goal. The low-level state handles the fine-grained, granular, step-by-step vector updates.
So if I'm understanding the geometry here, by separating the high-level goal from the low-level execution, the model avoids that brittle collapse we saw in Chain of Thought.
Yes, precisely.
If it hits a mathematical dead end in the low-level state, the high-level anchor realizes the trajectory is wrong. It can actually inject stochastic noise into the high-level updates to forcefully kick the computation out of a local minimum.
Right, allowing it to explore a completely different path to the solution all without ever outputting a single text token.
That is just brilliant. It allows the model to fluidly explore multiple plausible trajectories simultaneously. This is why GRAM architectures are suddenly dominating deterministic logic puzzles like Sudoku Extreme, right? Or the notoriously difficult RC-AGI spatial reasoning tasks.
Absolutely. Traditional LLMs collapse on those tasks because they commit to a faulty text token early on and just cannot backtrack. GRAM just continuously updates its internal vector until the constraints are mathematically satisfied.
That is amazing. But even GRAM looks traditional compared to the paper that absolutely stunned me while prepping for this deep dive.
Let me guess, the TRM paper.
Yes. The work on tiny recursive models, or TRM. The researchers took this concept of internal recursive looping and managed to build a functional reasoning network that has only 2 layers.
2 layers and exactly 7 million parameters. To put that in perspective, that is less than 0.01% of the parameter count of a standard frontier model.
It's literally a rounding error in terms of size.
It effectively is. Yet this 7 million parameter TRM achieved a 45% success rate on the ARC-AGI-1 benchmark, which, as you know, is the gold standard for testing true, generalizable, novel reasoning.
I am struggling with the physics of this. Because in deep learning, you need depth, right? Dozens, sometimes hundreds of layers to build abstraction. A 2-layer network shouldn't be capable of anything beyond basic pattern recognition. How is it pulling this off?
The breakthrough is a training technique called deep supervision, combined with massive temporal unrolling.
Temporal unroll.
Yeah. In a traditional giant model, data flows linearly through 100 physical layers to reach a conclusion. The TRM only has 2 physical layers, but it loops the data through those exact same 2 layers recursively, over and over again.
So it's trading spatial depth for temporal depth. It's using time as a substitute for silicon.
Yes, but the genius is in the deep supervision part. Because if you just loop a 2-layer network, the gradients usually vanish or explode, and the model forgets what it was doing.
Right, the signal gets lost.
Exactly. With deep supervision, the training algorithm actively supervises and corrects the model's internal latent state at every single step of the recursive loop. It forcefully aligns the internal representation at loop 5, loop 10, loop 50.
Wow. By tightly bounding the representation at every step, the model successfully emulates the computational depth of a massive neural network without the crushing memory footprint.
It is squeezing every drop of utility out of those 7 million weights. And if TRM is optimizing the individual model, the Disciple framework coming out of MIT CSAIL is optimizing how these models work together.
Disciple. Distributional constraints by inference programming with language models. It's essentially an advanced architecture for swarm intelligence.
It entirely rejects the premise that a single monolithic model needs to execute every part of a task. Disciple utilizes a self-steering architecture.
How does that work in practice?
You deploy one larger model, but you strictly limit its role to that of a leader. Its sole function is to parse the user's complex prompt, develop a multi-step strategic plan, and break that plan down into discrete, isolated constraints.
Okay, so it doesn't actually solve the problem, it just defines the parameters of the solution. It's not a super genius trying to build a skyscraper alone. It's the master architect drawing the blueprint.
That's a perfect analogy. And once the blueprint is drawn, it hands those discrete constraints off to a swarm of much smaller follower models, like an army of specialized Llama 3.21b models that act as the bricklayers and electricians.
They execute the actual mathematical legwork independently.
And because those follower models are incredibly small and fast, you can run hundreds of them in parallel.
Right.
The result is a swarm that generates far more accurate, logically sound responses than a single giant model, while consuming over 80% less compute.
This raises a glaring historical question for me. If a tiny two-layer network can emulate a massive one just by looping its own thoughts, or a swarm of 1 billion parameter models can out-coordinate a trillion parameter giant, why don't we start here? Did the entire industry just get blinded by the sheer novelty of massive data scraping?
Tunnel vision was absolutely a factor. When the initial scaling laws were discovered, the linear correlation between compute and capability was intoxicating.
Like a drug.
Truly. If adding 10,000 GPUs reliably increased your benchmark scores by 5%, there was massive institutional pressure to simply buy more GPUs. Rethinking the fundamental mathematics of the architecture introduces risk and timeline delays.
It was financially safer to build a bigger data center than to invent latent space recursion.
Exactly. But the reality of the scaling wall forced the innovation.
Which perfectly transitions into the physical constraints of this era. Because you can invent the most mathematically elegant recursive loop in the world, but if you try to run millions of temporal loops on the silicon we had in 2023, the chip would literally melt.
Oh, without a doubt. The software required a radically different physical foundation to execute efficiently.
This symbiotic relationship between software architecture and semiconductor physics has never been more apparent. By 2026, the hardware industry had to cross a monumental threshold to support these SRMs, the 2-nanometer fabrication frontier.
2 nanometers. We are talking about engineering at the scale of a few dozen atoms.
Which is insane. The quantum tunneling effects alone at that scale make traditional transistor designs completely unviable.
Exactly. The old FinFET transistor architecture, which basically powered the entire previous decade of computing, completely breaks down at 2 nanometers.
Because the gates are just too small.
Right. The gates are so small that they can no longer physically stop the flow of electrons. You get massive current leakage, which generates heat and totally destroys energy efficiency.
To solve this, TSMC, Samsung, and Intel had to commercialize gate-all-around, or GAA, architecture.
Where the gate literally wraps around all 4 sides of the silicon channel to physically trap the electrons and prevent leakage.
It provides unprecedented control over the electrical current. We are now manufacturing chips the size of a thumbnail that contain well over 50 billion transistors with highly specialized AI logic circuits etched directly into the silicon to accelerate matrix multiplication.
It's incredible. But GAA is ultimately just the absolute perfection of traditional digital logic. The true paradigm shift in 2026, the hardware that is genuinely built for recursive reasoning, is the commercialization of neuromorphic computing.
Right. We are finally seeing production-level chips that are biologically inspired. Systems like Sandia National Labs NeuroFem, Intel's Loihi 2, and brain chips Akita Pico.
Neuromorphic computing fundamentally abandons the synchronous digital logic that has defined computers since the 1940s. A standard CPU or GPU relies on a global clock, a rigid, oscillating metronome that dictates exactly when every single component on the chip processes data millions of times a second.
So it forces the entire chip to draw power simultaneously, regardless of whether a specific transistor is actually performing a useful calculation.
It's incredibly wasteful.
The best way to visualize that global clock is to think of a city's traffic grid. A traditional chip is like a city where every single traffic light is hardwired to a rigid global timer. It turns green, yellow, red, in a continuous loop, even at 4 a.m. when the streets are completely empty.
Right? Just burning electricity constantly, cycling through states, waiting for cars that aren't there.
Neuromorphic chips are asynchronous. They're like a city where a traffic light only activates and only draws power when a car physically rolls up to the intersection.
That asynchronous nature is achieved through spiking neural networks. These chips mimic the biological neurons in the human brain. They don't send continuous streams of ones and zeros. They communicate via tiny, discrete, binary pulses of electricity spikes.
So if the artificial neuron's membrane potential doesn't cross a specific threshold, it doesn't spike.
And if there is no data to process, that section of the chip draws absolutely zero power.
The energy efficiency is just staggering. We're talking about running complex inference tasks at sub-milliwatt power levels. But beyond the power draw, neuromorphic chips solve the most agonizing bottleneck in modern computer science, which is the von Neumann bottleneck.
Yes. The von Neumann architecture physically separates the memory unit, where the weights and data are stored, from the processing unit, where the actual math is done.
Right.
So every time a traditional GPU wants to perform a calculation, it has to physically shuttle the data across a bus from the memory to the processor, do the math, and shuttle the answer back.
And when you are running a tiny recursive model that loops thousands of times a second, shuttling that data back and forth burns more energy than the actual calculation. It creates a massive thermal traffic jam.
Neuromorphic chips eliminate the bus entirely. They co-locate memory and computation.
Wow.
The artificial neuron stores its own state and performs its own calculations simultaneously, directly at the edge. It is an architecture fundamentally designed to run the continuous latent space loops of an SRM without ever hitting a memory wall.
And the physical deployment of these sub-milliwatt neuromorphic chips sounds like pure science fiction to me.
Yeah.
Because they require almost no power and generate almost no heat, engineers in 2026 are embedding them directly into the physical infrastructure of the world.
They are. They are casting them into the concrete of highway bridges. They are weaving them into the carbon fiber blades of offshore wind turbines.
These neuromorphic twins run real-time, localized physics simulations, reasoning about the structural integrity of the material to predict microscopic stress fractures weeks before they actually occur.
It is the ultimate realization of edge computing. The intelligence is physically embedded within the sensor itself.
But this triggers a massive economic question. If these neuromorphic chips are acting like biological brains and companies are embedding them everywhere to run highly intelligent localized SRMs, how does this not completely decimate the business model of the major AI labs?
Oh, it does.
Because embedding 1,000 tiny brains into a wind farm is the exact antithesis of paying a massive monthly subscription fee to query a giant brain in a centralized cloud data center.
It doesn't just decimate the cloud-centric AI business model. It forces a brutal structural economic correction.
Let's run the numbers on this economic paradigm shift, because this is where the theoretical physics actually hits the enterprise balance sheet. In 2024, every Fortune 500 CEO panicked, assumed they needed AI immediately, and rushed to hook their internal software up to a frontier cloud API.
Yes, and they quickly discovered that routing everyday corporate logic through a massive general-purpose LLM is financially unsustainable. The unit economics of the cloud simply do not scale for high-volume System 2 workflows.
Give me an example of the math here.
Okay, take a standard mid-sized enterprise. They are running perhaps 10,000 internal AI queries a day, parsing unstructured legal contracts, matching invoices, resolving Tier 1 IT support tickets.
Very standard stuff.
Right. If they push all 10,000 of those complex queries through a frontier API like GPT-5, the token costs aggregate rapidly. They are staring down a monthly operational bill of roughly $4.2 million.
$4.2 million a month just for the privilege of accessing the API. It's an exorbitant operational tax.
Yeah, overlay the 2026 edge reality. That exact same enterprise pivots. They cancel the API contract and deploy a self-hosted, highly specialized 7 billion parameter SRM. They purchase an A10G GPU or a rack of neuromorphic accelerators for a one-time capital expenditure of around $6,000. Their ongoing monthly operational cost, which is just electricity and minimal maintenance, drops to under $1,000.
They go from burning $4.2 million a month in OpEx to under $1,000 a month. That is a 99.98% cost reduction. If you break it down, it's a 79 times differential per token generated.
It's unbelievable.
This isn't just an IT budget optimization. It is an extinction-level event for any company relying on thin API wrappers. You literally cannot survive in the market if your competitor is paying $1,000 for the exact same cognitive output that you were paying $4 million for.
And this isn't theoretical. The enterprise market has already adopted this. The Commonwealth Bank of Australia is currently operating one of the most sophisticated AI architectures in the financial
That's
sector.
right. I read about this.
But they aren't relying on a monolithic cloud model. They have deployed over 2,000 highly specialized local SRMs into production.
2,000 separate models.
Yes. And collectively, that local edge swarm is processing 157 billion data points every single day in real time. By utilizing these localized, hyper-fast models specifically trained for transaction analysis, they achieved a 70% reduction in real-time scam losses.
Wow.
They recognized that they didn't need an AI that could pass the bar exam or write a screenplay to analyze a transaction. They needed a structurally perfect, lightweight logic engine.
This realization has birthed the hybrid routing architecture that defines corporate IT in 2026. The smartest companies haven't abandoned the cloud entirely. They've just severely restricted its access.
Exactly. They route 90 to 95% of all daily queries to their local, essentially free edge SRMs. They act as the vanguard.
And the enterprise only escalates the top 5 to 10% of requests. The highly ambiguous, deeply strategic problems requiring broad world knowledge to the expensive cloud-based frontier models.
The center of gravity for AI computation has decisively shifted. Industry analysts confirm that roughly 80% of all AI inference now occurs locally at the edge.
But the shift isn't purely driven by the balance sheet, is it? Even if the cloud providers slashed their prices to zero to compete, they still couldn't win the enterprise market. Because edge AI possesses two insurmountable competitive moats that are governed by the laws of physics and the laws of governments.
Absolutely. The first competitive moat is latency. This is a strict physics problem.
Right.
If you are operating a high-speed industrial robotics cluster on a manufacturing floor or an autonomous vehicle navigating a busy intersection, you cannot tolerate a 200 millisecond round-trip delay to send sensor data to a cloud server, wait for the inference, and receive the command back.
No, a 200 millisecond delay at 70 miles per hour is a catastrophic accident. Edge AI executes inference in the single-digit milliseconds because the compute is physically millimeters away from the sensor. The cloud cannot move data faster than the speed of light.
And the second moat is privacy and data sovereignty. Following the enforcement of the EU AI Act, the tightening of HIPAA in the US, and massive corporate espionage fears, enterprises simply refuse to send their proprietary data over the open internet to a third-party server.
If we connect this to the bigger picture, data sovereignty is no longer just a checkbox for the legal compliance team. It is a fundamental structural advantage enabled entirely by small reasoning models.
Yes.
When a healthcare provider runs diagnostic inference on an MRI using a local SRM inside the radiology department, the patient's data never touches an external server. It effectively neutralizes the risk of third-party data breaches.
It provides total, hermetically sealed control. But here is the profound irony of the 2026 landscape.
Okay, what is it?
We have these hyper-efficient, incredibly cheap, perfectly private reasoning engines that fit on a local server. The technology is completely solved, yet the actual deployment is a disaster.
Really?
Yeah, the bottleneck has violently shifted from the silicon to the humans trying to manage it. We are facing a massive organizational crisis.
How bad is it?
Despite billions of dollars in capital expenditure, recent surveys reveal that only about 1% of major enterprises consider their operations truly AI mature.
Only 1%.
All right.
With all this technology freely available, why is the integration rate essentially zero?
McKinsey accurately diagnosed this as the last mile problem, which traps companies in what they call pilot purgatory. Getting a 7 billion parameter model to successfully analyze a dummy data set in an isolated IT sandbox is easy. The pilot always succeeds.
Right, but reality is messier.
Exactly. When they attempt to deploy that model across the live enterprise, it shatters. It fails because the enterprise lacks the underlying data infrastructure, the modern APIs, and the cross-functional management architecture to support the AI's actions.
Right. You can deploy the most brilliant latent space reasoning agent in the world on your local server, but if your supply chain runs on a 15-year-old proprietary legacy software system with no modern API endpoints, your genius AI agent can't actually do anything.
You can read the data, but it can't execute a purchase order.
It's a hyper-intelligent brain trapped in a paralyzed body.
Exactly. The plumbing simply isn't there. Realizing this, the entire startup ecosystem aggressively pivoted. Enterprises made it clear they no longer want to buy a raw language model. They want to buy a completed end-to-end workflow.
This birthed the era of agentic reasoning agents and digital process automation, or DPA.
This is where the massive venture capital is flowing. Look at Sierra. They hit a $10 billion valuation, not by building a better chatbot, but by building autonomous customer service agents that can navigate a company's fragmented internal databases to resolve complex patient authorizations without human intervention.
And Cognition AI's Devon agent hit $82 million in annual recurring revenue almost overnight, because it doesn't just suggest code snippets. It acts as a full-stack autonomous engineer that can debug, compile, and deploy. Harvey is doing the exact same thing for elite legal workflows.
And these DPA systems rely heavily on the multi-agent swarm architectures we discussed with the Takeover framework. Enterprises are deploying interconnected swarms of specialized SRMs.
How does that look at a workflow?
If a pharmaceutical company needs a clinical trial summary generated, they don't prompt a single massive LLM. They deploy a specialized data mining agent to extract the metrics, which automatically passes its output to a statistical analysis agent for verification.
Handing it down the line.
Right, which then hands the verified data to a medical writing agent for drafting, which finally passes the draft to a compliance agent to ensure regulatory adherence.
It's a completely autonomous, localized assembly line of intelligence. So for you, the listener, whether you are a project manager, a developer, or an executive, the mandate is glaringly obvious. The defining skill set of 2026 is no longer prompt engineering.
No, not at all.
Knowing how to write a clever prompt for a chatbot is a commodity skill now. The premium skill is system architecture and process integration.
Absolutely. The economic value is entirely concentrated in your ability to map a complex human workflow, identify the discrete decision nodes, and dynamically link specialized AI agents into those nodes using DPA platforms. You have to be an architect of automated logic.
But the successful deployment of these multi-agent swarms is acting as a massive destabilizing force on the human workforce, isn't it? The societal consequences of perfectly efficient, locally hosted reasoning models are hitting the labor market with unprecedented speed.
They really are. The most immediate and alarming socioeconomic impact is what labor economists are currently tracking as the graduate job drought.
It is a devastating squeeze on entry-level professionals. Historically, the apprenticeship model of white-collar work, whether you were a junior software engineer, a first-year legal associate, or a junior financial analyst, relied on you spending your first 3 to 5 years doing the low-level grunt work.
Right, you reviewed the legacy clone, you formatted the discovery documents, you built the baseline financial model.
You learn the industry by doing the tedious volume work. But today, a $1,000 a month local SRM swarm can execute that grunt work flawlessly in milliseconds, 24 hours a day.
Consequently, the bottom rung of the corporate ladder has been entirely sawed off. Employers are hiring significantly fewer junior staff. And for the rare junior roles that are posted, the requirements are completely inverted.
How so?
Entry-level candidates are now expected to possess the complex system architecture and AI management skills that were previously expected of a decade-tenured manager.
They are expected to manage the AI swarm on day one, without ever having learned the foundational skills the AI is executing. And this creates a terrifying training paradox. We desperately need to upskill the entire workforce to manage these systems, but our traditional educational institutions are completely paralyzed.
Yes. Last year, 68% of teachers in the U.S. reported receiving absolutely zero training on how to integrate AI into their curriculum. Meanwhile, you have the UK government taking a highly aggressive, active approach, launching a massive trial of AI tutoring systems for 450,000 disadvantaged pupils.
And to impartially review that data point, because we want to be clear here, it is crucial to understand the parameters of the UK trial. The deployment is explicitly designed and framed by policymakers as a supplementary tool, providing personalized, targeted assistance to students who lack access to private human tutors, rather than an attempt to replace human educators.
Right. It is a structural attempt to address educational inequality through automation.
Right. It's a fascinating contrast in policy approaches. But while the entry-level jobs vanish, a highly lucrative, bizarre new microeconomy has emerged for top-tier professionals. We are seeing the explosion of the AI training economy.
Because these highly specialized small reasoning models require pristine, mathematically perfect logic chains to learn from, companies can no longer rely on scraping random internet forms. They need elite human logic.
So AI labs and enterprise data teams are paying exorbitant premium hourly rates to veteran journalists, elite healthcare diagnosticians, and senior software architects.
Their entire job is to sit in front of an interface and act as the human master to an AI apprentice. They review the AI's internal reasoning chains, meticulously correct the logical fallacies, and provide perfectly structured examples of deep System 2 deduction.
It's highly compensated work, but it represents a deeply precarious economic dynamic. These elite professionals are, quite literally, architecting the precise logic loops that will eventually allow the autonomous swarms to replicate and automate their own highly specialized skill sets.
They are being paid handsomely to dig their own professional graves. And while the enterprise actively trains these models, they are fighting a massive, uncontrollable fire internally, which is the proliferation of shadow AI.
Shadow AI is the inevitable chaotic result of compressing frontier-level reasoning into 650 megabyte files. The democratization of this technology has completely bypassed corporate IT governance.
Just imagine being a chief information security officer right now. It is an absolute nightmare.
You spent millions of dollars locking down the corporate firewall, severely restricting access to cloud AI APIs to ensure sensitive data doesn't leak. And meanwhile, Dave, in accounting, is facing a brutal deadline for the quarterly financials.
So Dave just goes to an open source repository, downloads a 7 million parameter tiny recursive model onto a thumb drive, plugs it into his offline ThinkPad, and lets a super intelligent reasoning agent parse the company's unencrypted financial data.
And because that model is running entirely locally, completely severed from the internet, it generates zero network traffic. The IT department has absolutely no visibility. Dave finishes his work in 10 minutes, but he has fundamentally bypassed every data governance and security protocol the company possesses.
Which brings up a terrifying regulatory reality. When AI intelligence was strictly confined to billion-dollar warehouse-sized data centers, governments had a chokehold. They could regulate the export of the massive NVIDIA GPUs. They could monitor the API traffic.
But if a mathematically perfect, highly capable reasoning architecture can run on a processor the size of a postage stamp, completely offline, well, you literally cannot regulate the math. How do global regulators even begin to govern an invisible, localized intelligence?
They largely cannot, at least not using 20th century regulatory frameworks. The focus of safety, oversight, and compliance has to fundamentally pivot away from attempting to control the computation itself.
What's the alternative?
The new governance model must rely on zero-trust data architectures, focusing entirely on verifying the endpoints, strictly controlling where and how the output of any logic system, human or AI, is allowed to be applied within the physical world.
It is a profound loss of centralized control, and we are really only in the opening chapters of this era. So let's pull all of these threads together and recap the massive landscape we've traversed today. We have witnessed the definitive death of the bigger is better era. The tech giants hit the thermodynamic scaling wall, forcing a massive pivot to small-scale reasoning models.
We examined the mathematical breakthroughs making this possible. The abandonment of brittle chain of thought in favor of generative recursive reasoning within a continuous latent space.
We saw how models like TRM utilize deep supervision over temporal loops to emulate massive network depth with merely 7 million parameters, while architectures like Disciple coordinate swarms of these small models to execute flawless logic.
We tracked the hardware revolution that physically enabled this software, the shift from leaky FinFETs to 2-nanometer gate-all-around transistors, and the deployment of asynchronous sub-milliwatt neuromorphic chips that shatter the von Neumann bottleneck.
We outlined the brutal economic correction that followed, as enterprises realized they could replace $4.2 million monthly cloud API bills with $6,000 localized edge models, securing both ultra-low latency and absolute data privacy.
And we confronted the societal shockwaves, the graduate job drought stripping the entry-level workforce, the urgent need for process integration skills to manage multi-agent swarms, and the pervasive, ungovernable rise of offline shadow AI.
For you listening to this, the mandate for 2026 is inescapable. The competitive advantage no longer belongs to the company with the largest compute budget or the sheer volume of data. It belongs to those who understand structural efficiency, localized privacy, and how to seamlessly weave autonomous System 2 reasoning directly into the fabric of their daily workflows.
The intelligence is solved. The challenge is entirely in the architectural integration.
Exactly. But before we sign off, I want to leave you with one final, deeply provocative thought to ponder. It builds heavily on a theoretical discussion happening in cognitive science circles right now, known as the metacognition debate.
Oh, this is a fascinating area.
Throughout this deep dive, we've obsessed over how these small reasoning models actually work. They rely on recursive internal logic. They establish a latent state, and then they loop back on their own thoughts, continuously evaluating and correcting their own internal mathematical geometry before they ever commit to an external action or a text token.
Which is a functional mathematical mirror of what cognitive psychologists classify as access consciousness.
Right.
The ability of a mind to reflexively access, monitor, and adjust its own internal mental states.
Right. For centuries, human beings have placed ourselves at the absolute pinnacle of intelligence, and we've largely justified that arrogance by pointing to the sheer size of our brains, the massive density of our 86 billion biological neurons. We assumed consciousness required massive scale.
It's a natural assumption.
But if a microscopic 7 million parameter artificial network, a network that represents a fraction of the size of the giant cloud models we used to worship, can emulate deliberate, complex, deductive reasoning better than a trillion parameter giant, simply by turning its thoughts inward and recursively looping its logic back onto itself.
It is a humbling proposition.
Maybe human intelligence was never about the physical size of our biological hardware. Maybe true reasoning, and perhaps the spark of consciousness itself, isn't a product of scale. Maybe it's just a highly optimized, beautifully structured, recursive feedback loop.
If the essence of reasoning is simply the architecture of internal recursion, then it changes everything.
Then maybe, in the grand mathematical scheme of the universe, human beings are nothing more than biologically optimized, tiny recursive models. It is something to deeply ponder the next time you engage with a local agent, and you realize you are holding a perfectly structured, recursively reasoning brain right in the palm of your hand. Keep questioning the evolving logic of the world around you. We'll catch you on the next deep dive.